To build an empire, a state must move soldiers, calories, and information across its territory. If a message takes months, central authority collapses. Look at the Andean landscape. It lacks navigable rivers and virtually all flat plains. It is a continuous wall of vertical rock and deep ravines. This map outlines Tawantinsuyu, the Inca Empire, covering 2 million square kilometers across vertical terrain. Transitioning into a topographical cross-section of a 12,000-foot ascent shows why the wheel was useless. Sheer inclines guarantee the mechanical failure of any wheeled cart. Because the environment rejected the wheel, Inca engineers designed entirely different methods to move mass. They solved the friction of distance by maximizing the efficiency of bipedal endurance over mechanical transport. The only pack animal native to the Andes available to the Inca was the llama. This data visualization maps a llama's biomechanical limits, carrying 30 kilograms for 20 kilometers a day. When we scale that payload to match the demands of feeding and defending an empire of 12 million subjects, the supply deficit becomes obvious. Because individual carrying capacity was strictly capped by biology, the pathways themselves had to eliminate physical friction to prevent severe supply bottlenecks. The solution was the Qhapaq Ñan, a continuous, actively engineered logistical artery built specifically for the constraints of feet and hooves. In the Andean highlands, engineers paved the routes with cut stone and carved steep, stair-stepped pathways to conquer the elevation. The construction techniques adapted directly to the biome. Mountain paths relied on stone retaining walls and complex drainage channels, while coastal desert routes were built from compacted sand secured by adobe borders to keep shifting dunes at bay. This continental diagram traces the full extent of the resulting network, 40,000 kilometers of infrastructure, built around 2 primary north-south arteries and thousands of transverse routes. Constructing a project of this scale required the mita, a mandatory state-run labor tax imposed on the empire's subjects. Laborers carved zigzagging staircases into sheer cliffs by hand. They moved massive stone blocks without draft animals, executing physically grueling work at extreme altitudes. Sustaining that intense level of human exertion required immense caloric support from the state. The Inca stockpiled freeze-dried potatoes, called chuño, in tens of thousands of state-run storehouses, ensuring these laborers had a constant fuel source. The Qhapaq Ñan operated as a metabolically demanding machine, constructed and fueled by the physical taxation of the empire's citizens. The most severe bottlenecks in this road system were the deep river gorges that bisected the Andes. To span these impassable gaps, Inca engineers utilized large-scale tension engineering, building massive suspension bridges centuries before they appeared in Europe. The raw material for these structures was organic ichu grass. Communities executed a bottom-up construction process, braiding small grass threads into thin ropes and then twisting those ropes together to form 6 massive main cables. This schematic breaks down the bridge's tension dynamics. 4 base cables and 2 handrail cables span the gorge, anchored deep into permanent stone abutments. Overlaying load-bearing data reveals the extreme capacity of this organic tension engineering, supporting upwards of 16,000 pounds. But the design had a rigid biological constraint. Because the grass was organic, it decayed rapidly in the harsh Andean weather. To prevent the network from collapsing, the state enforced a strict maintenance schedule, requiring communities to completely rebuild the bridges every 1 to 2 years. Information travel in the ancient world was typically slow, but the Inca developed an elite runner system to transmit data at high speeds. They established a precise relay infrastructure. Way stations, known as tombos or chasqui, were positioned strictly every 2 to 9 kilometers along the entire road network. Runners, called chasquis, used a specific handoff protocol to maintain maximum momentum. An incoming runner sounded a conch shell trumpet, a pututu, alerting the next runner to begin sprinting alongside him, allowing them to transfer the data without stopping. Operating in shifts 24 hours a day, these couriers maintained a constant sprint, requiring elite lung capacity to perform physically demanding runs at 13,000 feet. By chaining human physical endurance together, the relay protocol formed a continuous high-speed data transmission line. The data payload carried by these runners was the quipu. These complex arrangements of knotted strings functioned as a non-alphabetic database, holding encrypted census data, precise tax records, and military directives. This animated map tracks transmission velocity. A message from Quito to Cusco covered 300 kilometers per day. Set against European horse-based postal metrics in a bar chart, the human relay is significantly faster, crossing 1,200 miles in under a week. This speed allowed the central government in Cusco to mobilize armies and redistribute food supplies and crush rebellions faster than any adversary could react. The Qhapaq Ñan weaponized the topography of the Andes, turning a hostile environment into an instrument of absolute state control.